and that will take to a point that the negative charge will collide with the positive charge, and that will collapse the atom, okay? So physically, the Rutherford atomic model is just impossible. It cannot exist because the attraction between positive and negative charge that will result in the electron colliding with the nucleus, and the atom would collapse. So that is a really big problem, and we have to tackle this problem, okay? So to tackle this problem, we will present a new atomic model. Okay, so what's the solution for our problem? Uh, the new atomic model, now called Bohr atomic model, uh, was studied by Niels Bohr, and for his contributions to the understanding of the atom, he got a Nobel in Physics in 1922. For the Bohr atomic model, there are some orbits that when the electron is in it, there is no loss in energy. Okay, so that's how Bohr solved the problem. He just said, okay, so we have some defined orbits here where there is an equilibrium between the electric force and the centripetal force, and that means when the electron is in this allowed orbits, there is no loss in energy, therefore they are stable, okay? So that was the idea behind the Bohr atomic model. Specific orbits where there is no loss in energy by the electron. Therefore, the consequence of the Bohr atomic model is that the electrons are organized in what we are going to call shells, okay? So each orbit we are going to call shell, and each shell will be divided in subshells. Okay, so one thing that I want you to understand right now. So let's look here at this picture. So we have here the nucleus at the center and the orbits around the nucleus. See here that the first orbit is smaller than the second, that's smaller than the third, and etc., etc., etc. So that means the number of electrons in the very first orbit has to be lower than the next one and lower than the next one. Because the orbits close to the nucleus are smaller, they cannot hold a lot of electrons because of the repulsion, right? So that means the first orbit will hold less electrons than the second, that will hold less electrons than the third, and etc., etc., etc. As we move far from the nucleus, we have larger orbits. Therefore, you can place more electrons in the orbits, and they will still be stable and able to handle that. This is a very important concept. So we know how to determine the number of electrons in any given atom. Now, what we are going to understand is how to organize these electrons in the different orbits. And that's our goal for today. Okay, so let's move on here to the next slide. Okay, so now let's talk about electron configuration, and I will show you how electrons are organized in shells and subshells. Okay, so later on in this course, we will call the subshells orbitals. So let's start with the shells. The shells are numbered between, sorry, the shells start with number 1, which is the one closest to the nucleus, and go all the way to number 7. So what I want to show you is how many electrons can we place in each shell. Okay, so let me write here a table. So I'm going to put here the shell number. And the second column in my table is going to be the max number of electrons in this shell. And I'm going to add a third column here later on. Okay, so leave a space here for a third column. Okay, so let's start with the shell number 1. So if we look at the atom, the shell number 1 is going to be the one closest to the nucleus. Okay, because this orbit is very small, the max number of electrons in the first shell is going to be only 2 electrons. Cannot have more than that. As we, second. Oh my God, I'm really sorry. Hold on. Oh man, Fridays are tough. Sorry about that. Now you can see what I'm drawing. Okay. All right. So shell number 1 is the one closest to the nucleus. Therefore, it's a small orbit. Only 2 electrons can go in the first shell. As we move farther from the nucleus, the next shell is going to be the shell number 2. So see now that the diameter of this shell is larger than the first one. So that means we can put more electrons in the second shell, and this number is going to be 8. And moving even further, so I'm going to draw here part of the third shell. Okay. So for the third shell, you have an even larger diameter, and that will increase the capacity, the number of electrons that I can fill there, and that number is going to be 18. The fourth shell is going to be capable of having even more electrons, and we can fill up all the way up to 32. The fifth shell is going to have 50, a max number of electrons of 50. The sixth, 72, and the seventh is going to be capable of having 98 electrons. Okay, so what I want you to understand to this point is that as we move far from the nucleus, the diameter of the orbit increases, and that will increase the maximum number of electrons that this orbit can handle. Okay, orbit here I'm naming as shell. Okay, so that's the maximum number of electrons that each shell can have. However, what we know is that all the way to today, some shells will not have the maximum number of electrons that they can have, and they will be limited to certain numbers, okay? So what we know to this point is that the shell number one, so let me put here in red, the shell number one, from all the elements that have been discovered so far, will have 2. The second shell will have 8. The third shell will have 18. Fourth shell will have 32. And then that's the point that things start to change. The fifth shell will have only 32. The sixth shell, 18. And the seventh shell, 8 electrons. Okay. So although the fifth shell can have a maximum number of 50, we have no knowledge of an element that has more than 32 electrons in the fifth shell. The same thing for the sixth shell. 18 electrons is the maximum number that we have found so far, and the seventh shell, 8 electrons. Okay. Therefore, what we are going to use for the number of electrons in each shell is what we see in the third column.
So the elements that, so we've never actually seen any elements or any atoms that have those amount of electrons. It's just kind of theoretical that we know they could include up to this, but it's just never been observed, correct?
That's correct. Exactly. Exactly.
Okay,
so,
thank you.
Yes, yes. We have not observed so far more than 32 electrons in the fifth shell, or more than 18 in the sixth, or more than 8 in the seventh. Yes, that's correct.
Following the pattern that we're looking at, is it possible there's an unknown element with an 8th shell that can hold 2 electrons?
Who knows? It might be possible. You cannot exclude that, because you can keep moving for more numbers here, but maybe somewhere there is an element that has an 8th shell and 2 electrons there. Then you close the pattern here that you are seeing. It remains to be seen, I guess.
So a higher shell can be have electrons in it, even though a lower shell isn't completely full to its capacity?
You can have this kind of situations. However, it's going to be
very rarely.
Very rare.
I'm getting ahead of myself here, right?
No, that's fine.
Okay.
and it's a state that's not stable.
Got it. Thank
Okay.
you.
Yes, no problem, no problem. Okay, so the reason why we don't see more electrons, for example, in the fifth shell or sixth shell or seventh shell is because if you add one more electron, you have to add more protons. And remember that the protons are in a very small volume and they have the same charge. Okay, so that results in instability. So that's why the heavy elements, they have a very short lifetime because they have so many protons in the nucleus that they are very unstable. Okay, so the heaviest element is the lifetime is lower than 1 minute, if I'm not wrong. So you have 1 minute to study the atom. Okay? And that's the reason why that's what we have seen so far. Remember here that this is a model and a model is never ideal. Okay, so there are limitations and the way you advance is to work on the limitations. Okay, so that's good enough for us to determine the number of electrons in each shell. Now we know that we can go from 1 all the way to 7, and you're going to have a max number of electrons of 2, 8, 18, 32. Then from here, you repeat 32 and start to go down 18 and 8. Okay, so now I showed you the max number of electrons in each of the shells. The next thing that I will show you is the subshells. Okay, so imagine the atom as being a representative of a state. The shells are the cities within the state, and the subshells will be the streets within the cities. Okay, so let's move on to the subshells now. Okay, so we know about the shells. Now let's get to know the subshells. I will show you 4 subshells. The first one is labeled as S, which comes from sharp, P, principal, D, diffuse, and F, fundamental. Okay. The first subshell S can have a maximum number of electrons of 2. Then for the second subshell, we have 6. Third subshell, we have 10. And fourth subshell, we have 40. Okay, and again, this is not limited to the F. You can have more subshells and then you add more electrons here. But what we know so far are elements with a max of 4 subshells. Now what I want to do with you is to determine the number of subshells for each shell. So to do that, I will repeat here the table that I draw in the previous slide. Okay, so I'm going to put here the shell number. The second column in my table is going to be the max number of electrons. And I'm going to add now a third column to my table regarding the number of subshells. And then we are going to do 1, 2, 3, 4, 5, 6, 7. We know that the max number of electrons for the first shell is 2. And then we have 8, 18, 32, 32, 18, and 8. Okay, for the subshells, we are always going to start from the S subshell and then move towards the F subshell. Okay. So let's think together here. The first shell can have a maximum number of electrons of 2. Okay? 2 is the maximum number of electrons that we can have in the first shell. First question, how many subshells we need to handle 2 electrons? If it's just 2, we just need 1 subshell. Which subshell can handle only 2 electrons? That's the S subshell, okay? So for the shell number 1, we only have 1 subshell, and that's the S subshell. Remember that we always start from the S subshell and then move towards the F subshell. If we move on to the second shell, now the maximum number of electrons is 8, okay? Because it is 8, we need, again, the S subshell, but we are going to need to add a second subshell, which is the P subshell, okay? So S can have a maximum number of 2 and P a maximum number of 6. The total has to be the maximum number of electrons in this shell, which is 8. Okay, are you following my line of thinking here? Okay, so now let's determine how many subshells are in the shell number 3. Okay, maximum number of electrons is 18. Always start from the S subshell. Here we can place 2 electrons. We need to add a P subshell that can hold 6 electrons. That's 8. And we are going to need to add a third subshell to hold the rest of the electrons. Okay, so 2, 6, and 10, that's a total of 18 electrons, and that's the maximum capacity of the third shell. So that's the idea that we are following here. Now for the fourth shell, we always need the S subshell. We will need to add the P subshell as well, the D, so that's so far 18, and the F subshell to complete 32. Okay, so the maximum number of electrons in each subshell, if you add them up, they have to be equals to the maximum number of electrons in the shell. For the first shell, we only have 1 subshell. For the second shell, we are going to have 2 subshells. The third, we have 3. The fourth, we have 4 subshells. And because the fifth shell has the same number of electrons as the fourth, we simply repeat the shells here. So SPDF, For the sixth shell, you cut down to 18. So that's going to be the same as the third shell, S, P, and D. And the seventh shell, you cut down to 8, S, and P. Okay, so those are the maximum number of subshells for each shell. Okay. To differentiate each subshell and indicate from which shell they are coming from, we are going to add one S for the first one. The second set of subshells, 2S and 2P. The third, 3S, 3P, and 3D. Fourth, 4S, 4P, 4D, and 4F. 5S, 5P, 5D, and 5F. 6S, 6P, 6D, 7S, and 7P. Okay, so the number in front of each subshell indicates which shell are you talking about. So if I'm telling you electron in the 1s subshell, you know that I'm talking about shell number 1. And 4s, for example, I'm talking about the shell number 4. Okay, so the goal here is going to be to determine how the electrons are distributed among each shell and subshells for any element in the periodic table. Okay, so let's move on. All right, so how are we filling up the shells and subshells? We are going to use the off-bow principle. That means the lower energy subshells are filled before the high energy ones. Okay. So we start filling the placing the electrons in the lower energy subshells, and then we move on to the high energy ones. How do you know which shell and subshell have the lower energy? So there are different ways to do that. The way I like is to trace diagonals like that. And I start from the top and move towards the bottom. And that will be the order that you fill the shells and subshells, okay? So start from the top, trace a diagonal towards the bottom. Once you hit this point here, you go back to the top and trace another diagonal. So that means the 1s subshell is the first one to be filled, and then you go back, and the next subshell to be filled is going to be the 2s. After the 2s, there is nothing after here. You go back to the top, and then fill the 2p, and then the 3s. So that will tell you the order that you are going to fill the shells. After the 3s, go back to the top, and then you are going to fill the 3p and 4s. After the 4s, there is nothing here to be filled. Go back to the top, and then you fill the 3d, 4p, and 5s. Go back to the top again, 4d, 5p, 6s, back to the top, and then again. Okay. Again, you don't need to fill up all the shells and subshells. Okay. So the number of electrons that you are going to put in an atom depends on each element. The way you are going to fill the shells and subshells is going to be according to the off-bow principle. First, start with the lower energy and then move towards the high energy shells. To determine which shell has lower energy than the next one, you trace diagonals, okay? And then you are going to start filling from the top of the arrow, going towards the bottom of the arrow. Okay, two important concepts here right now. The last filled shell in any given element is called valence shell. And the total number of electrons in that shell is called valence electrons. Most of the chemical reactions are going to deal with the valence shell. Okay, chemistry is a science of electrons, and most of the chemical reactions will work with the valence electrons. The valence electrons are the most exposed electrons. Those are the ones that will react. Okay, so let's work here with an example, and then maybe that will make things more clear, hopefully. Okay, so let's start with sodium. We know that the atomic number of sodium is 11. Okay, so Z here indicates the atomic number for sodium. Symbol of sodium is Na. And we know that the atomic number of sodium is 11. Okay, you can always go back to the periodic table if the information is not available. If the atomic number is equal to 11, that means we have 11 protons in this atom, correct? what's the number of electrons in this case? If you have no charge here, that means this atom is neutral. Therefore, the number of protons has to be equals to the number of electrons. Okay, 11 electrons in this case. So now the goal here from now on is to get all these 11 electrons and distribute among each shell and subshell. Okay, so that's what we need to be able to do from now on. So first thing is to determine the number of electrons. And now let's go a step further. Let's distribute those electrons among shells and subshells, and that will tell us the electron configuration for this element, for sodium. So use the off-bow principle, start filling from the lower energy subshells and move towards the high energy. So the trick here is to trace a diagonal. The very first shell to be filled is the 1s. We have a total of 11 electrons. However, the subshell 1s can handle only 2. To represent the amount of electrons in this subshell, I'm going to put the number right here as an exponent, okay? 1s2. That means we have 2 electrons in this subshell. So we are starting with a bag of 11 electrons. Let's distribute these electrons among the shells and subshells. The very first shell to be filled is the 1s, and the maximum number of electrons is just 2. So far, we distributed 2 electrons. There's still 9 to go. So we have to use another subshell. So go back here to the top and trace a diagonal. The next subshell to be filled is the 2s. The 2s subshell can have a maximum number of 2. So let's put here 2 electrons. So far, we have 2 electrons in the first subshell, 2 electrons in the second subshell. So that's a total of 4. We are still missing 7 electrons. So let's fill the next subshell. So go back to the top and trace another diagonal right over here. That means after the 2s subshell, the next one to be filled is the 2p. The 2p subshell can have a maximum of 6 electrons. Therefore, that's a total of 8 electrons in the shell number 2. So far, we have distributed 10 electrons, okay? However, we have a total of 11, so there is still 1 electron missing. The next subshell to be filled after the 2p, just follow the diagonal here, is the 3s. Attention to this point here. The 3s shell can have a maximum number of 2 electrons. It doesn't mean you need to fill all the way up. So far, we distributed 10, but we have a total of 11. Therefore, the number of electrons in the 3s subshell is going to be just 1. Okay? To indicate the number of electrons, you are going to use this exponent sort of notation. Okay? 3s1. That means you have 1 electron in the 3s subshell. And here you have just 1 electron in the third shell. Oops. Okay. So therefore, we have a total of 11 electrons. Okay. So this number here has to match with this number over here. Okay, now let's determine the valence shell. By definition, the valence shell is the last filled shell, okay? So for sodium, the valence shell is the shell number 3. So that's going to be called the valence shell. And it's very important to determine the number of electrons in the valence shell. Okay, the total number of electrons in the valence shell. In this case, we just have 1 electron in the valence shell. Therefore, we have 1 valence electron. Okay, so therefore sodium has a total of 3 shells, 1, 2, 3, and a total of 1 valence electron. Okay, those are very important numbers. Okay, so let's do one more example. So we will not have time to finish it, but let's start setting up the second example here. For example number 2, I want to determine the electron configuration for potassium. First things first, potassium, the symbol for this element is K. The Z here represents the atomic number. So therefore, potassium has atomic number 19, which means there are 19 protons in the nucleus of potassium. Because the charge here is 0, or this is a neutral element, the number of protons is going to be equals to the number of electrons. So for this case, we have 19 electrons. The next question is, how are those 19 electrons distributed among shells and subshells? Okay, so that's our goal from now on, is to determine the electron configuration for any element. To do that, you know the max number of electrons in each shell and subshell, and you are going to fill according to the Aufbau principle. So starting from lower energy and then moving to the high energy. Start always from the beginning of the arrow and move towards the head of the arrow. So we don't have time to do this today, so I will stop at this point and then we will pick up on Monday. Okay, so I think that's more than enough for today. It's a lot of information. So we will stop at this point, and I hope you have a great weekend, get some rest, and then come back on Monday ready to work.
Thank you.
Have a good weekend.
Bye-bye.
Thank you.
Good rest of your day.
Bye.
Thank you. Have a nice day.
Thanks, Professor.
Bye-bye.
Thank you.
Talk to you on Monday.